Hi folks, and welcome to Open Analysis Live. We're back 2 months off, and now we have a video that I hope is interesting for some of you. I know a lot of you have been asking for it. We're going to be analyzing Warzone Rat, which is a remote access tool. It's sold openly on the internet, so if you have some BTC, you can go purchase it. And it's used in a lot of sort of low-level criminal activity. We see it a lot with these sort of low-level credential stealing type campaigns. Now, the reason why it's taken so long to get to this video is because there's a lot of sort of basic blocks that need to be in place in order to understand how to reverse engineer this binary. So it's written in C++, and there's a few tricks that are used in it that need a little bit more explaining. So what we've done is we have produced a few videos over the past few years, actually, which will help build some understanding about what's going on here. So the first one is our Analyzing C++ Malware video. I'll link that in the description below. And another one is our RC4 encryption video, where you can learn how to reverse engineer RC4 encryption when it's used in malware. And then the last video is the one that we just released 2 months ago, talking about the microcode optimizations in IDA and how they can lead to some misrepresentation of the binary in the decompiled view in IDA. So all three of those videos, I highly recommend them before watching this one. They'll give you a lot of background. And if you feel like you're sort of missing some of the steps here in this video, go check those other ones out. Hopefully they fill in any missing gaps. So with that, let's just jump in here and we'll talk a little bit about Warzone. Warning, this video is very long, so I included some chapter links in the description. So like I said, it's sold openly on the internet, so warzone.pw. You can go and you can actually purchase a copy of this. It has all kinds of different features which you can build into it. So password stealing, download and execute stuff, remote shell. I mean, it has the works basically. It's pretty complete tool suite.
I don't know, it sells itself.
They also sell a cryptor, so they can encrypt it. I'll show you that in a second, and yeah, okay. They actually even have their own YouTube channel here, which I thought was interesting. Let me know if we should follow their YouTube channel. And they have 54 subscribers. Good job, guys. So what they do is in this YouTube channel, they have a couple of videos showing how to use the RAT, some of the features of it and stuff like that. So it's pretty popular. We see it used a lot in sort of like low-level credential theft campaigns and stuff like that. It does pop up a lot. We see it going through UNPACME quite often.
UNPACME.
And like I said, it's sold openly. So we've had a lot of requests to take a look at this just because of how prevalent it is and because it is kind of a pain to analyze, which I'm sure you guys will understand by the end of the video. And when I was first asked to look at it, I actually created a static configuration extractor for it. You can see this is 2 years ago when I first started looking into making a video for this. And I realized that in order to understand this completely, you need to have a few more foundational blocks. So it's been 2 years in the making, and every couple months we get another email or a DM over Twitter asking us to look at this. So finally we're doing it. Hopefully by the end of this video and maybe another follow-up video, you will have the tools to be able to write your own static config extractor for Warzone. So that's kind of the end goal here. And also analyze the binary or analyze any real C++ type malware. So in analyzing this, we went to our favorite site, UNPACME.
UNPACME, a malware unpacking service from Open Analysis. Expose the malware before it exposes you.
Where we basically had a sample here, we unpacked it, we can see we have a Yara hit. One of the antivirus industry names for it is AVE Maria, so that's why you see this Yara hit here for AVE Maria. If we were to click on it, just get some more information, go to Malpedia, we can see there's been lots and lots of blogs and reports about Warzone, and we can see up here in the aliases that is in fact, Warzone Rat, that is this Yara rule. So you can see pretty quickly, it's easy to identify, easy to unpack with UNPACME.
UNPACME.
And now all we need to do is just download the unpacked sample and go to work. So we've downloaded the sample. I'm going to open it up in IDA. We're going to do everything statically today. So it's going to be full static analysis. And the first thing we run into, and this is what we covered in our last video, is that there are some misidentification of function calls by IDA. And in our last video, we had one interpretation as to why this was happening. Again, we're just guessing at how the microcode optimizations work under the hood. Rolf gave us a really good explanation as to why we were wrong and a quick tip on how to fix this stuff when it happens. So let me show you the decompiled view here, and then I'll explain his tip and I'll show you how this works. So we can just press F5 here to get our decompiled view. I like to set it up split screen, as you guys know, and I'll just right click synchronize. There we go. And I like to view this as a text view. There we go. So if we go into, say, this function here, you can see that there's a lot of code missing from the decompiled view that's here in the disassembled view. Now, we covered this in our last video. The explanation we gave, I think, is incorrect in the video. My bad. Again, we were just kind of guessing at how the microcode optimization worked. But the problem was described correctly, which is that IDA doesn't have the correct parameters for this function call, and this leads to all kinds of other issues when they decompile the code. So unlike something like GITHUB, where they do a full decompile of the binary when you load it, IDA does a lazy decompile, which is why it appears so much faster, where it will only decompile the functions that you've opened. So right now, the reason why it doesn't understand the arguments that need to be passed to this function is because it hasn't actually decompiled it yet. It's only going to decompile it once you open the function. So what we can do is we can force IDA to decompile every function immediately, and that should fix any issues with these argument calls and not being able to identify the correct calling convention. So let's go File, Produce File, C File. So this produces a C source code like file using the decompiler for every function in IDA. So we'll create this, we'll just drop it in the temp directory here. And it's going to take a while. The reason why I think IDA doesn't do this automatically is because it takes a while to decompile every single function. And if you have a huge binary, this could take a lot of time. But it's pretty quick because this isn't a very large binary. And now that we've done that, if we come in here and press F5 again, voila, all of the code is there.
Wow.
They fixed all the incorrect calling conventions, which then fixed the microcode interpretation, which now shows up the code for Warzone. So it's just a quick tip that you can use for any binary you want, just to ensure that all the calling conventions, arguments, and stuff like that are correctly identified. And you don't have to go back and forth, decompiling and then going back into the function to fix it. So it does take longer, but in the end, you get correct results the first time. So quick tip, and thanks, Rolf, for pointing this out. Okay, now to the heavy lifting. So we now have decompiled our main section here for Warzone, and we need to start looking at how the binary is set up. So we know that they have an encrypted configuration file in there, because if we go to the strings here, we can see there is no IP addresses or host names or anything like that for their C2. So we're assuming that it must be encrypted somehow in the binary. We also know that because they're selling it, most likely they're using some sort of configuration file that's encrypted. And again, like I said, I've already built an extractor for this a couple years ago, so I know that there is an encrypted config that we want to look into. So usually, and this is just a guess because I've looked at a lot of malware, they'll try and decrypt the configuration closer to the entry point of the function, because they'll have to start using those values for the functionality. So usually we can find it pretty quickly by just starting and going linearly through the program. If this doesn't work, one of the tips that I think I've shown in some of the other videos is you find some network calls. So you find these APIs for things like, socket, open, connect, send, stuff like that. And you work backwards. So you know that they have to have an IP address or a host name when they use that API call. So you find that data, and then you just walk backwards from the calls until you find where the data actually comes from. And that'll be the configuration file. So there's two ways to do it. We're going to do it the straightforward way today because it's a little bit faster. And like I said before, I've already analyzed this binary, so I know that this is going to get us to the answer a little bit quicker. Also, now is a good time to give a quick refresher on C++. So
where do you come from?
I'm from the past.
So first off, what we need to do is we need to talk a little bit about classes and what they look like when you compile them. So here we have a simple C++ class, and it has two instance variables, width and height. And when you compile them, the concept of a class is actually lost. It doesn't exist anymore. and all you're left with are two variables sitting in memory somewhere. So like I said, in some cases, this is enough to analyze simple malware. If those variables are being referenced directly in the code, it's not a big deal. But you can come across some pretty interesting scenarios like this, where you have sort of a mystery variable. And this is, again, what will tip you off that you're dealing with some structs and some C++ is when you have these mystery variables. So what I mean here is, here's our class. We have a method for the class here where we multiply the width and the height to get the area of the rectangle, and we return that. So you have an area function, and the two instance variables here are multiplied together and returned. Now somewhere later on your code, you've already instantiated the rectangle class. I haven't showed that, and you're just going to call this area function or area method. So that all looks fine here, but when it gets compiled into assembly, and then IDA tries to make some sense out of it doing the decompiler, you end up with something crazy like this. So you guys have probably seen this before if you've looked at C++. You have a function, and passed to the function is a variable, a single variable, and then inside that function you will have a bunch of stuff happening with that variable. And it'll look as if that variable is an array. It'll look as if, you know, you're referencing that variable 1, that variable 2, etc., etc. So in that case, you definitely know something is not right here. And what's happened is there's an implied memory object that is passed to all of these calls, these class calls. So you have this as the class rectangle and the method area. So anytime you see this in C++, it's implied that the object memory for that class is actually passed into this function, which is why we see a variable being passed into the function here. Now, the problem is that IDA and the compiler, etc., don't know that this is actually a struct which contains the class variables. All it knows is that it's a pointer to memory, and that pointer is the very first variable in the struct. So what it ends up looking like in IDA is it looks like you're just passing a single variable to the class, and then once you get in the class, you decompile it, you look at it, and you see all these extra variables that seem to come from nowhere. You wonder, where did they come from? So that's really what's happening here, and it can be really confusing if you don't understand that, or if you haven't defined this as a struct. So now let's take a look at what happens when you tell IDA that this is actually a memory structure and it should treat it as a pointer to a struct, not a pointer to a single variable. So I'm going to show you how to do this in IDA in a second, but here I'm just showing you an example where we've done a struct definition of the two instance variables here, two ints, width and height, and we have now, instead of using int for this variable, we have defined it as that structure. So we've given it a struct definition. So what that tells IDA is that anytime that there's a pointer to this memory, it's a pointer to the whole struct, and it's not a pointer to just a single variable. Again, I'll show you guys this in IDA. This is just a quick overview so you can visualize what's happening. So what that means for our example that was confusing before, if we pop over to it. So now, when we see a call to this function here, instead of a pointer to var width being passed, we have a pointer to this, which is a struct that we've defined. So you can see here, it's a struct that we've defined. Now, whenever that struct is actually used in this function, it'll be referencing the variables within the struct correctly. And again, I'll show you that in a second. But this is the magic, basically. You have to sort of guess when you are going through this at what the struct size is going to be. Then you manually define it. It's kind of time consuming. There's a few tools for this, but none of them really work very well. I'm just going to show you guys the manual way to do it today. And so you manually define the struct. Then after you define the struct, you change the type of the variable that points to the first variable in the struct to be that struct. That's a mouthful. But basically you're just calling this a struct instead of a pointer to a variable. And then IDA will know anywhere that struct is used, okay, well, there's a whole bunch of variables here that need to be referenced, and it will automatically dereference them for you, which again, I'll show you in a second. So until we can start identifying and labeling those structs, it's going to be very hard for us to understand what the functions are doing. So the best way to do this, well, there's no great way to do this. There's a couple tools like Class Informer and stuff like that, which are used to do this automatically. I've never had a lot of great success with them. Not saying they don't work. I'm sure lots of people like them. But I'm going to show you a manual method here today. It's the same one that we used in our other video on C++ malware. And it's kind of slow going, as you'll see, but it does work. It gets you what you need in the end. So to do this, let's go and start looking at these functions. So we can see here is a bunch of API calls. Here's the first function call into the code. We can see that they're setting some sort of dword value, allocating a heap, and they store the heap here. Okay, well, they're not really doing too much here. So in order to save time later on, because this dword might pop up somewhere else, what I like to do is whenever I find something like this, a function which I'm not really sure exactly what its purpose is. Well, I know that's allocating some space, but I don't really know the reason for these values being stored or this heap. Is I'll just make a little note. I'll just change the name of the dword here, and I'll just change it to the number that it's being set. Press N for name, dword set to 32. Now, this is kind of janky, but later on, if I find out what the purpose of this value is, this global value, I will change the name. But for now, if I see this somewhere else, I'll know that I've already looked at it and I'll have an idea of what the value is in it. Same thing for this one. So this is allocating some heap space, so 128 bytes. I always use the MW underscore to preface any function that I label. This is just a way to separate the functions that I've labeled from other functions that are labeled automatically through tools or through IDA. So pointer to 128 heap. And I'm just going to name this setup heap. Okay, so all that's labeled. And again, I don't really understand what that's doing, what the purpose of that is yet. I just labeled it so that we have those values going forward. No use in ignoring it now because I don't know what it's doing and then having to come back and find it later on. All right, so our next function passes a few arguments here. Oh, interesting. Okay, so this functions. Yeah, because we can see that it is a pointer, and then each one of these, I guess there's no function on the first one, but each one is a function. When we come in here, we know that this argument here is pointer to functions. Okay, and something interesting here, so it looks like they're assigning that argument to this variable. If we press the equal sign, we can just say they're equivalent, no need to remap that variable. This sometimes can cause some issues if the remap variable actually matters, they're separate, but in this case, I don't think it's gonna make much of a difference. So now we can see, what are they actually doing here in this loop? They're looping through these functions, this pointer to these functions, which I had pulled up on the side here. So here's a list of different functions. They are looping through them and calling each one in order. So this is something that you'll see in C++. This is something that could be used for like inheritance or initialization of a class. When we want to analyze the functionality of the rat, we want to pay attention to these, but for now, I don't think we need to care about it because I believe that this will just be part of the initialization. So instead of wasting our time going in and trying to reverse engineer each one of these functions, we'll just put this aside for now and we'll take a look at it later on if we want to learn more about the functionality of the rat. What I'm going to do is I'm going to mark this call init functions, and that way we know that we've already looked at this, and if we need to look at it a little bit in detail later on, we can, and we'll rename this pointer to init functions. Okay, so the next function call we have is this one right here. So now we're going to have to start doing a little bit of reverse engineering. So it looks like there is a bunch of stuff being done on this function that we need to pay attention to. So like I said before, this is going to be a little bit tedious because we have to build these structs, and I believe this is where we begin to do that. So let's take some time and we'll talk about how to build them manually, and we'll take a look at this first function here, which I think is going to set us off. So we can see here that IDA thinks this is an array which is being initialized to 0. Now, we know that this is C++ and that there are going to be these structs or data structures which are being used as objects. So when we see something like this, what we want to do is we want to create a structure that represents this data so that we can actually operate on it instead of leaving it as just separate dwords in an array. It's clearly not an array, it's clearly some sort of structure. So the simplest way to do this is to just right click on the data type, reset it, then right click again and create new struct type. Now when you create a new struct type, IDA will try to interpret these different structure elements. Now what I like to do is I like to initialize everything as a D word. I fill in all these gaps and initialize everything as a D word, and then go back and fix it later. The reason why I like to do this is because this will set up a nice clean data structure with offsets that are easy to calculate. So 4 bytes by 4 bytes by 4 bytes, right? They're all D words. So this, again, this doesn't necessarily represent the data correctly right now, but it's a good way to start with a clean structure that you can then mark up later on and change. And it also helps when you have something like this. So what this means, see how it says gap 14? It means that IDA hasn't been able to determine what the data structure is for, or the data type, sorry, for that element. So it's filled in 8 bytes of random data just to make sure that the structure offsets are all correct. So what we can do here is we can just replace this with 2 D words. So we know 8 bytes, it's 2 D words. This is 1 D word, another gap here. Don't worry, I'm gonna fix the labels up in a second. And we don't need to get rid of this here. And there's a gap of 20. What's 20 divided by 4? It's 5. So we need 1, 2, 3, 4, 5 D words. All right. Make sure we have our semicolons everywhere. Okay, so now we have a structure that is composed entirely of D words. There is a label every 4 bytes, so every D word. And what we can do now is fix up the labels. Now, this is maybe controversial, but the way I like to do it is I like to do D words in decimal. So I like to have D word 1, D word 2, instead of using the offset, which is what IDA uses here. So IDA uses the offset, so it'll be like 0, 4, 8, blah, blah, blah. I like to use just a regular, 1, 2, 3, 4, 5 labeling scheme. Actually, I'll start at 0. 0, 1, 2, okay, and the name of the structure is also important because we're going to have a lot of different structures, and many of the times one structure will contain another structure. So it's important to have names for these. What I like to do before I understand what they are is just name them based on how many elements they are. So there's 19 elements of this one, so I'll just do a struct this 19, and that's basically it. So I've turned it into So this is a good actually example where I've missed this. So you can see how there's a this 1 D word 0. This means that the struct is too small for this data. I must have missed one of the D words when I was putting them in. So I'm going to go back and I'm going to add an extra D word to the structure so that it actually aligns correctly. Anytime you've created a struct and you see something like this where it looks like an array of this and then they assign a value to that element, it just means your structure is too small, and so you need to expand it a little bit. I must have miscounted when I added in the extra D words. So the way to edit this, or the best way to edit it, is to go to your locals view, not your structures view, and I'll show you why. It's because you can edit, now let's go to local types. It's because you can edit in C syntax instead of editing it as a structure. So you just right click edit, and we'll add an extra one on the bottom here, and we'll change this to 20. Okay, let's go back to our pseudocode here and change the label. Okay, yeah, there we go. So this has fixed it up now. What you saw me just do here when I clicked on this was I pressed the Y key, and that changes the type of the argument here. So I just changed it to be the new structure. Okay, so let's name this malware setup, or init struct 20. Okay, and we'll go back. So we now know that this value that was passed in is actually a structure. So IDA has helpfully relabeled this variable on the stack as the structure. So what we can do now is we can just name this as var struct this. Okay, so now anywhere that we see this passed in, we'll know that down here, we know that these are all the struct being passed into these functions. So we've already made this a little bit easier to read, and I think next up we'll have to start taking a look at this next function here. So it's got another it's got another structure. Okay, So let's do our trick first to create this structure, and then I'll show you what's going on here. This actually has what I was describing before, where you have a struct within a struct. So let's go reset pointer type, create new struct type, get rid of this. So IDA has helpfully created this structure within a structure. So we can say struct this pointer, struct this 20, and this, get rid of this here. And I'll relabel these so that it's using my labeling scheme instead of theirs. Okay, and then we'll name this as struct this 7. Okay, oh, looks like IDA kind of steered us wrong here. That's unfortunate. Let's go back to our local types here, and we'll have to fix this up. So it looks like this. Okay, and then F5 it. There we go. Okay, so now we've created that other structure, which I think I need to rename the name of it. Edit 11 or 12, sorry. Okay, and so this is going to be 12. Okay, okay, and then you can see IDA has fixed up this structure as well. And so what we'll do is we'll rename this structure here so that we can 12. Okay, so now we have two structures, two data types, which we can start adding labels to and reversing. They've been set up here, and this is sort of the most straightforward and least error-prone way I know to create these structures for C++ programs when you're reverse engineering them. Again, there are other tools that can do this automatically, but this way I think is pretty straightforward and intuitive. You just find the functions where they're initialized. You use the initialization offset to infer how big the structure is and what it looks like. Once you have that set up, you basically turn all the data types into D words, which is just to get started. Again, we'll fix those up later on if they end up being different data types later on. But just to get started, we turn them into D words. We add some labels to them so that we can figure out which offset is which. I use the base 10, 0 through whatever to label them instead of using the offsets, but it's whatever your preference. And now we have these structures, we can start understanding what this code does. So I can see here there's actually a bunch more code which we could probably look at. Looks like maybe they're getting the file name. What are they doing with the file name? Reading the file in. Interesting. What are they doing after they read the file in? Oh, are they doing some sort of hashing? What is that? Let's look up that constant. A murmur hash. Yeah. So they're creating some sort of murmur hash out of this. I wonder what for. What does this do? Allocate some heap space. Do a copy of the data. Let me guess. That's the event. Not equal to, let's look up that macro. Yes. Error already exists. So if the event already exists, if it doesn't already exist, they do this stuff. If it does already exist, oh, they exit. Do they exit? What's this? Is this like cleaning up? Close key? Yeah, clean up. This looks like cleanup time. Free? Yeah, okay. So just to recap, what I was doing quickly there is I was just trying to figure out what this code does. It looks like they read in the file, the malware file itself on disk. They create a hash of that file, and then they use that hash as an event. They create an event out of it, and if that event already exists, they exit the program. So this is sort of the same idea with mutexes, where you're using a known value to determine whether the malware is already running on the host. If it is running on the host, they exit. So in this case, they're using create event with the hash of the malware sample. Simple enough. So we don't really have to label that or get into how all this works. If I was writing a report on it, I might pay a little bit closer attention to, but you can see pretty quickly we can figure out what it's doing, so I'm not going to pay too close attention to it. If it doesn't exist, so it looks like this is where they actually do the functionality of the rat. So it's in here. Looks like they set some registry keys, and here we start getting into our structures here. So I think this is the first function we're going to start to analyze with the new structures that we created. So if we go into this function, oh, interesting. So if we go into this function, first thing I want to show you guys is that this argument is this struct here. So this is struct this 20. So if we go to this function, we can press Y in the arguments and change the type to struct this 20 and this to arg. Okay, so now we have markup for our argument, and let's use the N key to name our argument, arg struct this. Okay, so now we have references to that structure's data types in this function. So you can see already we're making a little bit of progress here. Simply by having that structure defined, we can now understand what's happening here. Now the reason why I was so interested when I opened this up is I saw this .bss. Some of you might recognize that as a standard name for a PE section. And if we look at the sections here, we can see there is a BSS section. Actually, let's take a look at that. Okay, so is this the configuration file? Yeah, I think so. Let's see what we have in the BSS section. So we have dword. If we create a dword here, that is 32. Then we have a bunch of it looks like encrypted data. So this is very possibly them reading in the P section BSS so that they can then extract the configuration from it. Now, like I said before, I have written a config extractor for this, so I know that this is actually where the config is. But when I was writing that config extractor, I didn't even create the structures or go through any of this. I just took a wild guess that this was BSS because I saw it here. So, you can sometimes circumvent this stuff, but we'll keep reverse engineering here as if we didn't know that and see if we can't make some sense out of what we see here. So what else was passed into this function? Let's go back. They pass in a 0, eh? I'm just gonna say, not really sure, maybe it's some sort of flag or something like that. I'm just looking here to see if I can make an equivalence mapping, which I think I can. That looks good. And let's see if I can make an equivalence mapping here, and I think I can. Press equal sign, yes, it's fine. Okay, so now I'm starting to get back to some readable code. Let's see what they're doing up here. Looks like initializing something. Yeah, it looks like this is a keep alloc into 0. So I'll say wrap heap alloc. It looks like whatever they pass in here is another structure of sorts. X. So it looks like this is some sort of structure of sorts, which they then pass in here. Probably worth. Oh yeah, interesting. So it looks like they're reading on a PE file here. If I just press R, I can recognize that's MZ, that's PE. So it looks like maybe they're reading some data in here. Let's take a closer look at what's going on here. Okay, this is very interesting. Okay, so you will sometimes see functions like this in malware, which is mapped in memory and trying to understand some reference to where it is in memory. So here what they've done is they've basically assigned the address of this function here, which is itself, to this variable. Then they have this, see this MZ90, that's the header for the PE file. So let me just pull this up in a hex view here. I'll open the Warzone file, and you can see the first 4 bytes here, 3 bytes. First 3 bytes here are MZ90, and so that's what we've got here. We've got MZ90, and so what they're doing is they're checking to see whether the bytes at this offset are equivalent to those MZ90 bytes. So let's just rename this as malware check bytes equal. And we'll pop back here. So while they're not equal, they continue to search backwards from this address. So this V0 is we'll just name this pointer to a memory offset. So they basically search backwards through memory looking for MZ90. And essentially what they're trying to do is they're trying to find the offset to the beginning of the PE file, to their own PE file, so the Warzone malware, as it's mapped in memory. So what they do is once they found that, they return the address of it. So we're going to call this malware find PE start. So this is going to be var PE or PE address. So It's kind of an interesting function, and you'll see it sometimes with malware that needs to locate itself in memory. I believe the reason why they're doing this is so that they can find the BSS section, right? So now that we see that this is the address to the beginning of the PE file, it looks like we're gonna have to try and figure out at least a little bit about what this data type is here. So let's go back in here and we'll try and build a rough struct for it, just so that we have some sort of reference for that other function. So it looks like we have at least 15 D words in here. So let's create a structure in our locals here with at least 15 D words. So what we'll do is we'll edit one of these guys, just copy it, cancel, right click, insert, paste. It'd be 15, 0 to 14. So it's 11, 12, 13, 14. So 0 to 14 is this guy, struct this 15. Okay, we come in here and we will do a Y, and this will be struct this 15. Okay, oh, looks like we're 16. Yeah, I think it's 16. Annoying. We gotta edit it again.
I'm fast as fuck, boy.
Okay, so now we have that structure built. Malware init struct 16, and we'll go back now, and now we have this, and so we'll have to label this as well. So this should be name var struct this 16. Okay, so now we have a structure to work with here, and we should change this structure as well. 16. Okay, struct this. It's very tedious doing all this, but it makes the code so much more readable. So you can already see it's much easier to see what's going on here. Oh, it looks like this structure is actually a little bit bigger than what we thought. Remember, we see the 1 here, so we are going to have to adjust it again. I'll come in here, edit. Again, it just, you just continuously adjust as you go, make these things look a little bit better, a little bit cleaner, and eventually you'll get to the point where it's completely clean. There we go, that cleaned that up. Where it actually has a data structure that you can use to properly reverse engineer this. So the other interesting thing here that I want to point out is we know that the second arg here is the beginning of the PE file in memory. So we can name this arg PE address. So we can start labeling these now. So this D word here, we'll just name it as PE address. And so you can see now already these structs start to take on a little bit more meaning, because as you label them, it makes more sense what they are. Now here we see something interesting. We know that this is a PE address in memory, but why would it be being referenced like a structure? Well, PE files are actually composed of a bunch of different data structures. And if we were to pull up the MSDN PE header format, you can see that the header is composed of a series of data structures which are nested with other data structures. So what we can do is those structures are actually, they exist in IDA, and so what we can do is we can just relabel this as a different structure. We can press Y, and of course this would be the DOS header, so it would be image DOS header. And so now we can see that the offset here, ELFANEW, is actually the pointer to the PE header start in a PE file. So actually, if you guys didn't know that, you could look it up here. So you can see this value contains the file offset of the PE header. So we know that that offset plus the beginning of the PE file gives you the PE header. So this variable here is the PE header address, and the type is image NT header, right? So now this starts to make a lot of sense, because the signature of the PE header is PE. So this starts to match up now, and we can start to make sense of the code that we're seeing here. We can see the machine type whether it's 32 or 64-bit. So this is var PE machine. And so we can see if it's a 32-bit machine, we do this code. If it's a 64-bit machine, they use this code here. So by adding in those structure types, the code becomes infinitely more readable, and you can start to make sense of what's going on here. So I think because this video has gone on for a long time, what I'm going to do is I'm going to use the magic of cinema to finish marking up the structures in IDA. And when we come back, we'll continue reverse engineering the binary with the labeled structures, and we'll attempt to find the configuration file and decrypt it. So with that, let's use the magic of cinema.
Much later.
And there we go. So now I've gone through and labeled all of these structs, but as you might have noticed from the light change and my new libation, it's been a while. So what I think I'm going to do is I'm going to probably wrap up the video now. I'll quickly go through the structs that I've added here, and I'll leave you guys with an IDC file which I'll produce from this database, which you guys can then import into your own database and continue the work. So let's go through those structs right now. So what we've done here is you can see I've actually labeled the function copy PE data, and we can see now we have added some labels to our struct here because we figured out what the data is that's being copied over. Probably the most important one is the fact that we've copied over these sections from the PE file. So we've copied pointers from each section into our struct, which we're going to use later on. Also, you'll see that these variables here, as I've added type information to them, they've displayed very nice here in IDA. We can actually see what values are being read instead of just that weird long array of random variables that you saw a minute ago. So by adding in that type information and labeling this struct, we've made this very readable, and we can figure out now that what they're doing is they are looping through the number of sections in the PE file, and they're copying the section data into our struct here, this struct that's being passed in. So they're basically just making a copy over of the section information into our struct. So if we go back, you'll see that I've also marked up a few of these functions here. Don't worry, I didn't go too deep. All I did was I added the type information just like I was showing you before, and I added labels to our structs. So this will speed up the reverse engineering process quite a bit. As you can see here, a lot of our data types now have structures assigned to them, and because of this, they are very easy to read in the IDB. We can see exactly what's going on. So this is really the key when you're reversing C++. As we described in our other video. If you take it step by step, you add the type information and you create structures and label the structures, you'll be able to turn basically an unintelligible mess of code into something that looks very readable, very easy to understand. So what I'm going to do is I'm going to create an IDC file. So this is a script file that can be run in IDA that captures all of this struct information and type information. And I'm going to link it in the description of the video below. So what you guys can do is you can go and download this unpacked copy of Warzone, and you can run that IDC script. I'll show you how to do that in a minute, and populate all of the type information that I've added into your IDB. So in the end, your IDB should look like this, and that'll basically bring you guys up to the point where I am here. So for today, we're going to wrap it up. I'm gonna drink my beer, and what we'll do is next video we'll go through identifying where the configuration file is. We already kind of know it's in the BSS section, but I'll show you how to confirm that, and also we'll use the type information and the struct definitions to figure out the structure of that encrypted data and how it's decrypted. So I mentioned before, a little spoiler, it is RC4 encryption, but you don't know where the key in the data is. And I'll show you why it's very important to understand how the structs are set up in order to get that information. So stay tuned for that next video. Right now I'll show you how I export the IDC type information, and I'll show you quickly how to import it yourselves if you want to work on this in between the two videos. So for me to export it, I just go File, Produce File, Dump Database to IDC file, and I'll just call it warzone.idc, and that'll be what's linked in the video below. Now I'll show you from your perspective, if you want to apply this type information to your database, what I'll do is I'll start a new fresh IDB with Warzone without any type information or anything like that, just a plain Jane what we had at the beginning of the video, and I'll show you how to import that IDC script and run it to populate the type info. Okay, so we have our example loaded up here. So this is what it would look like if you loaded that Warzone sample in your IDA and you had done any reverse engineering. So all we have to do is we have to go to File, Script File, apply the IDC file. You'll see it'll spit out a bunch of stuff at the bottom here as it applies the types. So all you have to do to find that function that we're just looking at is just come over to your function window here, Control F, decrypt, and it was called decrypt config. So we'll load that up, press F5, and we have all of our structure information here, all the types, all of the functions are labeled. So you should be able to basically add all that information that I've just shown you in the video into your IDB so that you can basically start reversing at the point where we are now. So for right now, I'm going to leave it there. And in the next video, we'll pick up and we'll figure out how to decrypt this configuration file, how to implement that in Python, and then do a little automation to show you how to do sort of a quick Warzone tracker type thing. So stay tuned for that. I hope you guys found this interesting and applicable. There's lots of malware out there that uses C++. They have this type of multiple structs and type information that you need to add in to reverse it. So having this in your toolbox is probably going to be helpful, at least at some point in your career. So with that, until next time, keep exposing the mechanics behind the malware. Stay curious.
Yeah, you know you fucking feel me. Yeah, you know you fucking feel me. Yeah, you know you fucking feel me, right?